Good evening, sir.
Good evening, students. So I'll start with the new topic, that is our cutting temperature. Okay. All right. So to continue with, we previously discussed about the cutting forces. Okay, and the measurement of cutting forces using the analytical method. Analytical method means using some formulas or equations to calculate the value of the cutting. We have seen three cases. One is
क्या हो गया?
depending on the deflection. I'll request you to please mute yourself because there is sound coming from your end. Okay, thank you. So depending on the deflection, because the cutting force is directly proportional to the uh, deflection in the tool. Second is the kind of pressure, and third is the strain. We have already discussed that. And again, regarding the cutting forces, how to measure it using experimental process. Just give me a minute, I'll to take this call. Hello. Hello. ওকে ওকে ঠিক আছে, দেখে নিচ্ছি। হুম, ওকে ওকে ঠিক আছে। Okay, I was facing some issues regarding creating the test. Okay, so I have a test which has been created. Okay, I'll let you know about the time. Okay, so let me continue. So the cutting temperature is your temperature which is generated during machining process. Okay, so now if we look into the details of why cutting temperature is necessary for us to understand, okay, or why this temperature is generated. Okay, normally we know that the machining takes place due to the interaction between the tool and the workpiece, and there is some of the material which is removed due to plastic deformation and shear, and some friction also comes into part. So due to this friction element, there is some amount of heat which is generated on in the tool work zone. So some heat is developed and temperature is generated in machining. Okay, so we'll discuss about the effects of the cutting temperature on both cutting tool and the job, and how it can be measured by analytical and experimental methods, and what is the again it's coming up, what is the method of or what is the role of variation if in case we vary the different parameters, measuring parameters, as in we can consider the feed speed, depth of cut, that is those are the measuring parameters. We have the tool geometry in place, we have your workpiece and tool material in place. These are the things which we can consider as machining parameters. And also one very important thing, that is the cutting environment, that is what kind of cutting fluid we are using, whether or not we are using any cutting fluid. Okay, these are the things which we need to consider in order to determine what kind of, or what are the roles of these variations on the temperature which is generated. Okay, so what are the things that we need to do for controlling the parameters, that also is a major concern. Now if you look into this part wherein we have this workpiece and the tool interaction, so there are three zones basically. This zone is called the primary shear zone. Okay, this zone, primary shear zone, as we have already seen that there is a shear plane, and along the shear plane the primary shear zone is there, so where the major part of energy is converted into heat. Okay, why this major part is converted into heat here? Because there is some kind of plastic deformation that takes place. Okay, now when there is the chip is moving away and it's rubbing at this place, that is 2. Okay, and there is some amount of friction which is generated here, and this is a secondary deformation zone, right, which we can call at the chip tool interface. So the chip, as it is moving away, it rubs with the rake surface of the tool, and there is some amount of temperature or heat which is generated, and the maximum heat is carried away, as you can see, by the chip. So there is heat generated on the chip end as well as on the tool end. In primary shear zone also, there is some amount of heat which is generated at the chip end as well as at the workpiece end, that is the unmachined surface. So unmachined surface any which ways will be removed in the form of chip. Okay, only some amount of heat is you can say retained at the workpiece end and at the flank surfaces, that is the worn out flanks, due to the rubbing action of the tool and the finished surface. Now this happens due to incorrect flank clearance angles. In case of flank clearance angles, if you remember, we have discussed while discussing about the tool geometry that the importance of flank clearance angle. So in case the flank clearance angle is not provided properly, or the flank has worn out in some case due to any reason, due to multiple use of the tool, that is the most probable reason, and that is when the tool rubs with the machine surface of the workpiece, and there is a chance of generation of the cutting temperature in this place. Okay, so primary shear zone is number 1, where the major part of energy is converted to heat. Secondary deformation zone is at the chip tool interface, where the further heat is generated due to the rubbing or shear. And finally, at the worn out flanks, because normally flank do not come in contact with the machine zone. In case it has worn out, then only it rubs with the tool, with the machine surface, and the heat is generated. Okay, all right. So now next thing is, as you can see, that the maximum, as I told you, the maximum amount of heat is carried away by the chip. So the heat generated is shared by the chip cutting tool and the flank. This is not blank, this should be flank. Okay, okay. The apportionment of the sharing that heat depends upon the configuration is a size and thermal conductivity. This is very important, that what is the thermal conductivity of the tool, what is the thermal conductivity of the workpiece. Okay, because depending on that, sharing of the heat matters. Okay, so as you can see here from this diagram, that the depending on the cutting velocity, okay, the share of heat changes. So as you increase the cutting velocity, the most amount of heat is carried away by the chip. Okay, okay, blank here, blank we can consider as you see here, blank is your workpiece. Okay, blank, normally this term we use uh, in terms of like some material which has to be worked upon, that is called blank. You have also heard about this in your uh, mm, press tool operations. Okay, so that is what we are calling as blank. Blank is a workpiece, the chip, tool and workpiece. Workpiece is your blank, right? So from 10 to 20% of the total heat goes into the tool, and some heat is absorbed in the workpiece. So with the increase in the cutting velocity, the chip shares heat increasingly, right? So as you increase the cutting velocity, the amount of heat is carried away by the chip, or most amount of heat is taken by the chip. And since it would be removed from the machining zone, so we can say the maximum heat is thrown away in the form of chip or along with the chip, if in case you are using a higher cutting velocity. That is a cutting velocity of around or more than 100 meter per minute. Okay. Next, let us come to this effects of high cutting temperature on the tool and job. Okay, so the effect of cutting temperature particularly is high and is mostly detrimental. Detrimental means it's harmful to both the tool and the job. The major portion of the heat is taken away by the chips, but it does not matter because the chips are thrown out. So attempts should be made, as I just told you, that the chips normally are thrown out. Okay, that is why the uh, main issue is that the detrimental effects are less in case of the tool, in the case of the workpiece than the tool. So tool are more affected rather than the workpiece. Okay, so attempts should be made that the chips take away more and more amount of heat, leaving the small amount of heat to harm the tool and the job. So what are the detrimental effects on the cutting tool, or rather the edge, cutting edge? That is, we encounter rapid tool wear, which reduces the tool life. Plastic deformation of the cutting edges if the tool material is not enough hot hard and hot strong. So what is hot hard and hot strong? That means at a elevated temperature, the tool should not encounter plastic deformation. Or normally what we, in the forging process, what we do, we heat the material and then we apply some amount of force to deform it. So that means a material has a tendency of getting deformed at a higher temperature, right? So if the tool is hot hard, that means at a higher temperature also it maintains the hardness, it do not get deformed, or rather we can say that it do not allow anything to penetrate itself. And also it is hot strong. Okay, so thermal flaking and fracturing of the cutting edges due to thermal shocks. Thermal shocks, as in sudden rise and fall in temperature, may lead to thermal flaking, that is in the form of flakes. If you see that there are some old walls, okay, from the old walls, paints are removed in the form of flakes. Okay, so that happens in case of the cutting edges of the tool if they are encountered by thermal shocks. Okay, and again built up edge formation may take place in case there is higher heat. What is built up edge formation? Built up edge formation is the joining of the uh, workpiece with the tool, that is workpiece or rather the chip of the workpiece with the tool rake surface, and they get converted in the form of a weld, and some of the material is removed from the rake surface and we see crater wears coming up. Next is the uh, possible detrimental effects of the higher cutting edge on the tool edge are dimensional inaccuracy. Uh, this should be job. Please excuse me on this and please change it accordingly. So we have already discussed about the tool edge, cutting tool edge. This is about the job. So dimensional inaccuracy of the job due to thermal distortion and expansion contraction during and after machining process. Surface damage by oxidation, definitely, since high temperature is like the tool, the workpiece surface is in contact with high temperature as well as in contact with the atmosphere, it may get prone to oxidation and rapid corrosion and burning may take place. So induction of tensile residual stresses and microcracks may be generated on the surface and subsurface of the workpiece material. Now, what happens? This higher temperature at times we require to reduce the cutting forces. Suppose there are few materials which require, which are very hard, okay, and which have very high amount of shear strength. So what happens is it becomes difficult for a tool to penetrate through it and remove the material. So at times, higher cutting temperature helps to reduce the, or we can say reduce the shear strength or make the material soft and in order to reduce the magnitude of the cutting forces. So less cutting forces can easily cut the material, and also cutting power consumption becomes low in case of higher cutting temperature, right? So we also call this technique as hot machining. Okay, and in for very hard materials, this kind of process or hot machining process can be used. Next is the determination of cutting temperature. The magnitude of the cutting temperature. Why we require to know the magnitude of the cutting temperature? Because to know whether the workpiece that we are trying to machine, whether it is machinable or not. Okay, that is the amount of cutting forces, the temperature, tool life that are in place, whether using those things the product or the workpiece will be machined or not. It is whether it is possible to machine that or not. Okay, design and selection of cutting tools. Evaluate the role of variation of different machining parameters on the cutting temperature. Proper selection and application of the cutting fluid. This is a very important thing. That is, for a certain combination of tool and workpiece, whether I am using a proper cutting fluid. As you have heard that while machining cast iron using a high-speed steel tool, HSS tool, we do not require any lubricant from outside, any liquid lubricant we do not, or liquid lubricant or rather cutting fluid we do not need to use. So what is the reason behind this? Because in cast iron, graphite is already there in the form of solid lubricant. Okay, because carbon percentage in case of cast iron is much more, and it acts as a solid lubricant. It forms in the it helps in the form of graphite. It gets converted into form of graphite. Okay, or rather we can say the carbon present in the cast iron is in the form of graphite, and the while machining, while removing material from this cast iron, that carbon comes out of the material and acts as a solid lubricant. So we do not require any kind of extra lubricant to be added. Okay, or any kind of cutting fluid to be added. And then what is the process or method of application of this cutting fluid? That is also a very important part. Next is analysis of temperature distribution in the chip, tool and the job. The temperatures which are of major interest are the average shear zone temperature, the average and maximum temperature at the chip tool interface. So as you can see from the first one is the average shear zone temperature. This relates to the primary deformation zone, or we can say this part, primary shear zone or primary deformation zone. At the deformations or at the shear zone, the primary deformation is taking place here. Okay. Next is your average and maximum temperature at the chip tool interface. So chip tool interface is a secondary deformation zone, and the maximum temperature is at the chip tool interface. And finally the theta f is the temperature at the tool flanks, worn out flanks. So these are the three things, very easy to remember. If you remember the 3 points where, or 3 areas where the temperature, major temperature generation takes place. Okay, the principal main means primary shear zone, that is and second one is the secondary deformation zone, and third one is the at the worn out flanks. So you have all the 3 things in place. Then the average cutting temperature, the average of all of these. Okay, now the cutting temperature can be determined by 2 ways: analytically, that is using some uh, theoretical equations, some relations. Okay, and then experimentally by the use of some thermocouple, some experimental setup. Okay, analytical methods are not really that much accurate, because they again do not give us a real-time picture of what exactly is happening. However, experimentally, we can find out the details of or the exact value of the temperatures. Because see, experimentally, when we perform the machining, it may not happen that the temperature is constant, the temperature which is generated is constant throughout the machining process. It may change or vary. Okay, which you will not be able to get in case of any kind of mathematical expression or mathematical models. Mathematical models will give you a specific value for a certain, like suppose you have some input variables and you have the output variable as a cutting temperature. So when you put the input variables in the form of a formula, okay, you will get the output variable as a constant value depending on those input variables. Okay, so definitely you will not get a varying result. However, in experimental value, you will definitely get a varying result, because the uniform contact or uniform, like whenever the machining process is taking place, okay, the uniformity in generation of the cutting temperature will not be there. Okay, then the analytical estimation of the cutting temperature, normally these two values are found out, that is at the shear zone and at the chip tool interface temperature. Excuse me. So if we look into the experimental methods of the cutting temperature, so among the three, the maximum or the highest temperature is at the chip tool interface, and the experimental methods generally provide the average or maximum value of theta I. As I told you that it will change constantly as the machining is going on. So you will get a average value or maybe the maximum value that the temperature rises to. So some techniques are also enabled to get the distribution of the temperature in the chip, tool and the job at the cutting zone. So if we look into the analytical estimation of the cutting temperature, then we can use some equation to find out the average shear zone temperature. So we know that the cutting energy per unit time is PZVC. Okay, PZ is the cutting force into cutting velocity is the energy which is consumed per unit time. So this is the, we can say, the power, cutting power. Okay, that is used to cause the primary shear and overcome the friction at the rake face. So the PZVC is equals to PSVS plus FVF. Okay. Now, what is VF? VF is the velocity at which the chip flows. Okay. And VS is the velocity along the shear plane. Okay. So if you put these values, you will get some relation here, that is PSVS equals to PZVC minus FVF. Okay. Now equating amount of heat received by the chip in 1 minute from the shear zone and the heat content by the chip, it appears that AQ1 into PZVC minus FVF by J equals to CV. CV is specific heat. Okay, A1, B1. A1, you know, it's the uncut chip thickness. B1 is the width. VC is the cutting velocity. Theta S minus theta A. These values are given here, as you can see. A is the fraction of shear energy that is converted into heat. Okay. Next is your Q1. Q1 is a fraction of heat that goes into the chip from the shear zone. J is equals to the mechanical equivalent of heat of chip and work material. CV is the volume specific heat of the chip. Theta A is the ambient temperature. A1, B1, as I told you, is the uncut chip thickness, and B1 is the width. So A1, B1 is the cross sectional area of the uncut chip, which can be also written as T. T is your depth of cut into feed. Okay. So if we put this value, okay, or rearrange this in such a manner so that we can get theta s in the terms of the other known values. Ambient temperature is also known to us. So we will get a relation here in this manner, that is AQ1 into Pz minus F by zeta. Zeta is your chip reduction coefficient, that is A2 by A1 divided by J T S naught. J is what? J is the mechanical equivalent of heat. Okay. So generally A varies from 0.95 to 1 and Q from 0.7 to 0.9. Okay, inch in case of the turning operation, right? So these are the values which you can put, and you will be able to get the value of your shear zone temperature, okay, from this analytically. Next is your theta I, that is the temperature at the chip tool interface. So using the two dimensionless parameter Q1 and Q2, now there's a Buckingham relation which we use, that is Q1 equals to C1 into Q2 to the power n, where Q1 is CV theta I EC. EC is specific cutting energy, CV is specific heat at constant volume. Then Q2 is VC CV A1 by lambda. Now lambda is what? Thermal conductivity of the material, to the power minus to the power 0.5, that is under root of this. Okay, so and here n is a index which is close to 1.4, 1 by 4, 1/4. Okay, so therefore we can find out the value of theta I, and we can get this relation from this relation. Okay, that is C1 EC under root VC A1 divided by lambda CV. Okay, so these are the values we can get analytically, that is theta s and theta I we can get analytically from these equations. However, as I told you, these values are not accurate. However, in order to get the accurate values, we will require to go for the experimental methods. So the experimental methods are calorimetric method, okay, which is quite simple, low cost, but not very accurate. Okay, normally it gives a average value. Then we have a decolorizing agent, some paint or tape. Now if you apply some paint, what will happen? Due to the temperature rise, the change in the paint will take place. Color will change due to the heat which is generated. Then we have tool work thermocouple. Okay, simple and inexpensive, but gives only average or maximum value. Then we have moving thermocouple technique, embedded thermocouple technique, using compound tool indirectly from hardness and structural transformation, photocell technique, infrared detection method. So I'll quickly show you these things, mostly theoretical in nature. Okay, so experimental methods of determining the cutting temperature. So amongst these three, that is the theta s, theta I, and theta f, theta I is the highest one, and mostly this can be measured using the experimental methods. So some techniques also enable to get the distribution of the temperature, which was discussed earlier. So tool work thermocouple technique. So as you can see here, there is some kind of insulation here, some copper brush, okay, and from here it is connected in such a manner. So this is the tool, this is the work, and the thermocouple acts as there's a millivolt meter, and which shows some amount of deflection. Okay, so which, as I again, the similar process of transducing, that is temperature value getting converted into some voltage value, that voltage is further amplified to find out what is the value of the temperature that is being generated. Okay, so this is the basic idea. So in a thermocouple, two dissimilar but electrically conductive metals are connected at two junctions. Whenever one junction is heated, the difference in the temperature at the hot and the cold junction produce a proportional current which is detected and measured by a millivoltmeter. In machining process like turning, the tool and the job constitute two dissimilar metals and the cutting zone functions as a hot junction. Then the average cutting temperature is evaluated from the millivolt after thorough calibration for establishing the exact relation between millivolt and the cutting temperature, right? So here again we have the thermocouple, okay, wherein some oxyacetylene torch is used, okay, with a copper plate, okay, and here you can see there's a carbide rod, so there's a millivoltmeter which is connected, okay. So this is a method of calibration of measuring average cutting temperature in turning steel rod by uncoated carbide tool. So if you are using some uncoated carbide tool, you can calibrate using this, because calibration is again very important. Without calibration we will not be able to get proper results, okay. Next is moving thermocouple technique. In moving thermocouple technique, what happens, this enables a measure of the gradual variation in the temperature of the flowing chip. Like as I told you that the chip takes away the maximum amount of heat. So as you can see here, the thermocouple is connected to a point where the chip has not yet been removed. It is the uncut chip, okay. So as it will be removed, you will get the difference in the temperature, okay. So before it reaches the shear plane, the temperature will be recorded. After it enters the shear plane and then crosses the shear plane and moves out, so the entire process, you will get the value, okay. So here what happens is, a bead of standard thermocouple like chrome alumel is brazed on the side surface of the layer to be removed from the work surface, and the temperature is attained in terms of the millivoltmeter, okay, in millivolt. Now in embedded thermocouple technique, in operations like milling, grinding, etc., where the previous methods are not applicable, embedded thermocouple can serve as a purpose. Standard thermocouple monitors the job temperature as a certain depth, HI, from the cutting zone. The temperature recorded in the oscilloscope or strip chart recorder becomes maximum when the thermocouple bead comes nearest, slightly offset to the grinding zone. With the progress of the grinding depth, the HI gradually decreases. After each grinding pass, the value of the temperature, theta m, also rises, okay. So now for getting the temperature exactly at the surface, that is at the grinding zone, okay, HI has to be 0. Xi went up, which is not possible, okay. So theta m versus HI curve has to be extrapolated up to HI equals to 0 to get the actual grinding zone temperature, okay. So this is the embedded thermocouple technique. So as you can see, the log graph has been drawn. So this is what we are getting, okay. So the difference, you can see there's a graph of the theta m and the HI, right? Similar kind of log graph here, okay. Next is measurement of chip tool interface temperature by compound tool, okay. Now in this method, like a small piece of conducting tool piece, carbide, is embedded in the conducting tool of ceramic, right? So because if in case you are using some non-conducting material as a tool like ceramic material, okay, then what will happen, you will not be able to transmit the uh, heat, okay. The conduction of the heat will not take place. Therefore you have to connect some material, conducting material, okay, which will be embedded in that tool, and it will carry the temperature to the millivoltmeter, okay. So the conducting piece and the job from the tool work thermocouple, which detects the temperature theta I at the location Li of the carbide strip. Thus theta I can be measured along the entire chip tool contact length By gradually reducing Li, Li is the this length of the tool. Okay. So if Li is reduced, then theta I can be measured along the entire chip tool length. Okay.
So
However,
last 2 minutes left, sir.
sorry.
Last 2 minutes left, sir.
Okay.
The session will be.
So calibration has to be done properly before that. Last one is a photocell technique. Okay, photocell technique, unique technique enables accurate measurement of the temperature along the shear zone and tool flank. Right. So you can use the photocell technique for this. Next is the infrared photographic technique. Okay, infrared photographic technique can also be used. These are mostly theoretical things, okay, which you can do a self study. In case you have any doubt, you can get in touch with me. I'll explain. Okay, next one is the role of variation of various machining parameters on cutting temperature. We'll discuss this in the next class. I'll let you know when the next class will take place, and also we'll discuss on the different type of cutting fluids and how cutting fluids are applied. Okay.
Sir, do we have any test on this session?
Yes, you will have the test. I was trying to create the test, however, was facing some issues. So once I am able to create the test, I'll send you in the WhatsApp group. Okay, please try to keep a watch on the WhatsApp group. Okay, I'll give you around 20 minutes login time and 15 minutes duration of the test. 5 questions you have to answer. Okay, and accordingly, I'll be able to take the attendance for today. Okay, thank you. Thank you so much for attending the class. Okay.
Yes.
Thank you. Have a good day. Bye.